So today I will talk about percolation, especially in random graphs. And on Friday I will give the last lecture on 0-1 laws. But I should say if you are afraid of logic, so am I. It's really about playing games. So the nice thing for me to do these 0-1 laws is to define the Ehrenfreund game, as has been done in earlier talks, and then you want to analyze certain combinatorial games. And so it's really going to be combinatorics and probability. So that will be on Friday. So the title is the Erdős-Rényi phase transition, but I will also talk about other phase transitions because this is a very important and very general concept. So let us begin in 1960 with the great paper of Paul Erdős and Alfred Rényi on the evolution of random graphs. In their model, they had a random number of edges, and they, in our modern language, they saw that there was a phase transition when the number of edges was n over 2. So if the number of edges is Cn, where C is less than 1/2, for example, 0.45 n edges, then all the components are small. This is in a random graph, so of course I mean with high probability. But if you then have 0.55, if you go from 0.49 n edges to 0.51 edges, there is a phase transition, and a giant component of size positive proportion of the vertices has occurred. And they also discovered that at n over 2 edges, the size of the largest component was on the order n to the 2/3. And this they called the double jump. But that's a nice term historically, but we look at it a little bit differently today. So here it is in the traditional way. Instead of counting number of edges, let's use probability. So P equals C over N. When C is less than 1, it is subcritical. So all the biggest component is of size log N. And all the components are simple. By simple, I mean mostly they're trees, but you might have one cycle. They might be unicyclic. That I call simple. Going to the bottom, when C is greater than 1, there is a giant component. This is what it was called by Erdős-Rényi, whose size is y times n, and y is a function of C. It's a positive number. And all of the other components are of size at most log n, and they are simple. And in the middle, at C equals 1, the biggest component has size on the order of n to the 2/3, but its actual distribution is quite complicated. And furthermore, the second largest component also is of order n to the 2/3, and they have a complicated joint distribution. And furthermore, the complexity of the component. By complexity, I mean edges minus vertices plus 1. So a tree has complexity 0. A unicyclic has complexity 1. Those are the simple ones. Bicyclic has complexity 2, etc. And the complexity also has a non-trivial distribution. So very complicated. And if you've worked in percolation, you know that when you're right at the critical point, things are very critical, complicated. And that's the case here. Now today, we look at it in 5 phases. This was the great advance in the 1980s and 90s. That the critical window, so you say P equals 1 over n. At first you say, well, look, P equals C over n. There are only 3 possibilities. Either C is less than 1, or C is greater than 1, or C equals 1. No, No. We have a second order term, so we take the value c equals 1 and we stretch it out. But how do we stretch it out? The great advance was n to the minus 4/3. The critical window, we write p equals 1 over n plus lambda n to the minus 4/3. Lambda can be positive or negative. And for any constant lambda, this is called the critical window, where things are very complicated, and we'll talk about that. So now we think of 5 phases: subcritical, with it like Erdős-Rényi, c is less than 1; supercritical, where c is greater than 1; but barely subcritical, if we have 1 over n minus n to the minus 4/3 times lambda of n, where lambda of n is going to infinity, then that's called barely subcritical. And if it's 1 over n plus lambda of n, n to the minus 4/3, where lambda of n is going to plus, sorry, this is with a plus, then that's called barely supercritical. And these will have very, very different, they will look very different, as we'll see in a moment. So now instead of 3 phases, there are now 5 phases. Basically, the barely supercritical looks like subcritical, and the barely subcritical looks like subcritical, and the barely supercritical looks like supercritical, as we will see. So what happens in the barely subcritical, and actually let me mention, this is wonderful for computer experimentation. If you know algorithms, instead of using probability p, you put in the edges 1 by 1. There are algorithms to keep track of component size. There's something called union find. They're very efficient algorithms. So you can start with 500,000 vertices. Each time I say this, I have to add another 0. And just randomly add in edges. And the subcritical, think of lambda equal 4. So if you stop at p equals 1 over n minus 4n to the minus 4/3 as a proportion. So proportion and probability are about the same. If you stop with a proportion 1 over n minus 4n to the minus 4/3, what you'll see most of the time is that the top components are about the same size, and that all the components are trees or unicyclic. And the scaling for the top components is n to the 2/3, So if lambda equals 4, you'll see that with the scaling, they're all around 0.05, but maybe the top one is 0.05, the next one is 0.04, 0.03. They're all close together. But technically, we should let lambda of n go to infinity. Formally, we let lambda of n go to infinity. But actually, take lambda of n equal 4 in a computer experiment, and you'll see it quite clearly. Then the barely supercritical. Yeah.
K. Can you say something about K?
For any fixed k, so let's say we want the top 10 components. Yeah, this then gets more complicated, yeah. If you want k to go to infinity, that's more complicated. But if k is fixed, then it's okay. So the formal thing is, if k is fixed and lambda of n goes to infinity, then the top k components all have about the same size, yeah. But when you reach lambda equals plus 4, or really lambda going to infinity, what has happened is these components have joined together. And then you'll see that the biggest component is much, much bigger than the second biggest component. And it's very nice on the computer simulation. I mean, this is really fun to do, and I really encourage you to do it. There will be the top component I call it the dominant component. It's still not giant, but it's much bigger. Sometimes I call it Ceres for the, the asteroid, the biggest asteroid. So it's not yet Jupiter, but it's Ceres, okay? So a little astronomy there. So this biggest one might be 10 n to the 2/3, and it will not be a tree or unicyclic. It will have some reasonably high complexity, still, but constant. And all the others, so maybe the biggest one is 10 n to the 2/3, and then the second biggest one will be 0.1 n to the 2/3. And all the other ones will be simple. It's interesting. In this critical window, at a certain point, the second largest component becomes smaller. How can the component become smaller? How can the second largest component become smaller? It merges with the first largest component. So then you have, and that effect, after a while, becomes more. Of course, the components are getting bigger, but you have two effects. The components are getting bigger, but then the second component merges with the first component, and so the second largest becomes smaller. And as you go through the critical window, later on, that second effect becomes important. What's happening is all the components are merging with the dominant component. There's an interesting gravitation. There's really like a physics going on here. It's a wonderful, wonderful picture. And I should say, yeah, no, that's what I should say. Okay. Let me give some other things in percolation. Percolation is a huge topic. In math physics, there is bond percolation. If we think of it in terms of graphs, we have the grid on ZD, and we put in an edge with probability P, but the physicists say the bond is open. And then there's a critical probability P sub C, and when P is less than P sub C, all the components are finite. And indeed, if you look at the component of the origin, I mean, all the points look the same, the component of the origin, it has an exponential tail. When you're supercritical, you have a unique infinite component. This was actually quite hard to prove that it was unique. It was proven. And if you look at the component containing the origin, its expected value is infinite. Although if you condition on it being in a finite component, it has an exponential tail. And then one looks at criticality, and at criticality, all the components are finite, and the expected size of the component of the origin is infinite, but the distribution has a heavy tail. And then physicists look at what happens when you're epsilon away from criticality, and there are critical exponents, and there are a lot of results. So the physicists look at this infinite model. We're looking at an asymptotic model. What are the analogies? The finite components, the word finite here for the infinite model, the analogy is at most logarithmic. So the analogy to finite is at most logarithmic. See, of course you're going to get a component of size log n because you've got n places you can start. So somewhere you're going to just be lucky and get log. It's like you'd flip log n heads or something. And on the other hand, the infinite component corresponds to a finite proportion of the vertices. So these are just analogies. These aren't theorems, but these are the analogies. Here's another one, a great problem that remains very open. Random 3 set. You take a random clause of size 3, and you take m random clauses and you ask what is the probability that it's satisfied, and we know that m should be something like 4.1 times n seems to be the right thing. We don't know it exactly. In fact, indeed, we don't even know that it's uniform, but we believe that there's a constant c so that criticality occurs. Maybe, let me call it 4.1. The criticality occurs when you have 4.1 n clauses. If you have more clauses, it won't be satisfied. If you have less clauses, it will be satisfied. But then the question is, what is the critical window? So as a function of m, you look at the probability that it's satisfied. At some point, the probability is 10%. At another point, it's 90%. How far is it from where the probability is 10% to where the probability is 90%? And we don't know. That's, to me, a big open question. In percolation, I think there are two questions. Where is the percolation point? Of course, that's the more natural question. But I think the more important question is, what do things look like near the percolation point? What's called the critical window. Here's one that I and many other people have worked on. Take the n cube, that is, you have 2 to the n vertices. Sometimes it's called the Hamming cube. 2 to the n vertices, and you join the edges if they differ in one coordinate. And then on that graph, put in edges with probability p. Then the critical point is at 1 over n. So Nicemerity is here, and he had one of the early important papers on this. If p is 0.99 over n, you're not going to get a large component. In fact, the biggest component is basically logarithmic, not in n. You have 2 to the n points. Logarithmic in the size of the graph, which is 2 to the n. But when c is greater than 1, when the probability is 1.1 over n, then you get a giant component. In fact, that was proven by Nicemerity, Komlosh, and Aitai. And then there was a paper by Bolabash, Wuchak, and Kohayakawa. And then I had a paper with Christian Borgs and Jennifer Slade. Sorry, Christian Borgs and Jennifer Chase and Remco van der Hofstad. All three were here at different times. And Gordon Slade at University of British Columbia, where we did some further work, to try to understand what does it look like near the critical point. What does it look like near the critical point? And we have a lot of results, but it still remains an interesting topic. Here's another nice one that I've worked on and many other people have worked on. This is a process called the Bowman-Fries process for Tom Bowman and Alan Fries, both at Carnegie Mellon University. It's one of many similar processes, so the specifics aren't so important. You start with the empty graph, and every time you're going to add one edge. Every round you add one edge. Now here's how you add an edge. Randomly, there are 2 edges, x1, y1, x2, y2 are generated. You look at x1, y1. If x1 and y1 are isolated, then you take that edge. And if not, you take x2, y2. There's no x3, y3. That's all you. So in a way, it's the simplest way to change Erdős-Rényi. But it's been the object of a lot of study. I mean, there are many similar things. These are called Aklioptis processes for Dmitry Aklioptis, where the idea is that in each round there are 2 random edges, and you get to select one. You select one of those two edges and you add it to the graph. But this is a specific process, and along with Nick Wormald, who's now in Melbourne at not the University of Melbourne, the other place in Melbourne, which he was at University of Melbourne, but he went back. He's at the other school in Melbourne. And we found where the critical point was. That is, we found a proportion T over N. That's proportion, not proportion. Proportion T over N. So if with Erdős-Rényi it's T equals 1, here it's not T equals 1. The giant component is delayed because we have a tendency to join the isolated vertices. But we were able to get some differential equations to model the structure, and we were able to find the exact point of criticality. That is, if you're earlier than that by epsilon, then the largest component is order log n. If you're bigger than that by epsilon, you have a giant component. So we were able to show that. And then there's been a great deal of study of the critical window. Myun Kang, who's in Graz. Will Perkins, who was my student, who is just going to Birmingham in the fall. Bamidi, Buttaraya, and Wang, who are at North Carolina. And Sen, who was a student at Courant, who's I think he's going to Bonn, but maybe to the Netherlands. I don't know. He's going somewhere. And so there's a lot of work on the critical window, and though we don't have a total 100% picture, it looks like Erdős-Rényi. That is, the critical exponent is n to the minus 4/3. So P should be, the P should be the critical value plus lambda times n to the minus 4/3, so that we know the width of the critical window. There's been a lot of. Here's one that we really don't know. The process sounds similar. Again, each round you get two random potential edges, and you check the number of points in the component of x1 times the number of points in the component of y1. And you compare that with the other edge. And whichever is smaller, so it's the product of the component sizes. Whichever is smaller, you add that edge. Now, this is a very powerful anti-gravity, because if you have two medium-sized components, their product is big, and you're very unlikely to add the edge. Of course, eventually you'll add the edge. But what happens is, this process, it goes and it goes and it goes with a powerful anti-gravity, and then finally it just explodes. And it's just amazing. So along with Raisa Desusu and Dimitri Aklioptis, we had a paper that didn't have any theorems in it. My first paper, and what a catastrophe. Maybe it was a good catastrophe. Because when we did the simulation, it really looked like the size of the giant component was going from 0 to 60% in 0 time, where time means the number of rounds divided by n. So we thought, in a limiting sense, it would really be 0 time. Because we looked at the graph of the size of the largest component, and it would go like this, and then suddenly, like with a million vertices in 200 rounds, suddenly it was 60% of the graph. So we conjectured that it was explosive percolation, which sometimes called first order percolation. That is, it would go to a positive proportion in 0 time, but sorry, I can't say his name, Dorogovtsev, close enough, who is in, where is he? He's in Russia and somewhere else.
In Portugal.
He's in Portugal, but he also has a place in
Yes, yes, in St. Petersburg.
in St. Petersburg. Yeah. Okay. So he with his co-authors gave a physics argument, saying no. While it looked like it was discontinuous, it really was continuous. And then Oliver Reardon and Kurt Warnke actually showed with a mathematical proof that indeed it was continuous. So our simulation conjecture was definitely wrong, but we really don't know what it does look like. I mean, what the critical window does look like, and it remains a fascinating question. So I want to say that there are all these different processes where you get to criticality and you want to understand, what does the critical window look like? How do you go from no large component to the giant component? What is the way to look at that critical window? Okay. Now I want to talk about Erdős-Rényi, and I think the purest thing, we start with the Galton-Watson process, the Poisson birth process. So we start with some vertex Eve, and Eve has Poisson C children, and then they have Poisson C children, and then they have Poisson C children. And maybe it keeps going, or maybe it dies. We don't know. And this is called the Galton-Watson process, but I'll call it the Poisson birth process. The way I like to look at it is as follows. Eve has her children, which is Poisson means C, and then she dies. And then we take the next person. Of course, maybe it ended. Maybe she had no children. But then we take the next child. Think of it as breadth first search. We take the next one. She has Poisson C children, and then she dies. And then the next one has Poisson C children, and she dies. So if we look at the population size, it starts with 1, the step size, and at each step you have Poisson C children, and then you die. So that you can think of this like a random walk that starts at 1, and this is the step. And if you reach 0, well, then the process is dead. But actually, I prefer to think of fictitious continuation. In terms of analyzing it, even though the process is actually dead, we can think of it this way. So, and the size is the first place where it hits 0, but the size might be infinite. The size might be infinite. So t equals infinity means that it never hits 0. Now, if c is greater than 1, it's got positive drift, so it may drift off to infinity. If c is less than 1, it's got negative drift, so it's got to hit 0. It's got to hit 0. Now, a second process that's almost the same is, instead of Poisson birth, we let the number of births be binomial MP and do exactly the same process. But when M is large and P is small, and MP is C, then binomial M, which is moderate, then binomial MP is pretty much the Poisson with mean C. So we have this intermediate thing which turns out to be useful in the graphs, But basically, for our purposes, we'll just think of this as the Poisson birth process. Now comes the graft process. So what happens in the graft process, let's take a particular point and look at the component of the point. And we'll see it looks like a birth process. So let's find the component by using breadth first search. So we take this point and we see how many neighbors does it have. Well, the number of neighbors is binomial n minus 1 comma p. Now I'm going to think of p as c over n. So this is going to be like Poisson. So it's going to be very much like the Poisson picture. It's going to have 3 neighbors. And now we look at this, and maybe it has 2 neighbors, and we keep on going. So that the study of the component, starting with a single point, looks very much like the birth process, except until it gets successful. Until it gets successful. This is called ecological limitation. Notice this process, you have to stop at n vertices. You only have n vertices. But the birth process can go on forever. So what's the difference? The difference is when we got to this vertex, it wasn't binomial n minus 1p. It was binomial n minus 4p, because we have to look for new vertices. Now, binomial n minus 1p, binomial n minus 4p, they look the same. But after a while, if we're successful, and the more successful we have, we always have to find new vertices. So if we've already found 1/10 of the vertices, now it's binomial 9/10 np. So it starts to die out. And so that's the critical difference. The birth process and the graft process look the same until the graft process is really successful. And then the graft process has an ecological limitation. Now, the birth process is very well understood. If c is less than 1, we have negative drift, and t is the number of the total population, the total number of children, number of points in the tree, and that's going to be finite. And if c is greater than 1, then we have positive drift. Of course, it might die out. In fact, Eve might be childless with probability e to the minus c, but it might die out later. But with positive probability, it's an infinite structure, When c equals 1, that's the critical point. So each node has Poisson 1 children and then dies. So there's 0 drift. It's on the average, it's having 1 child and then it dies. So what happens then? Well, actually everything's known, we'll come to it. With probability 1, t will be finite, but it has a heavy tail. We'll see exactly what it has. In fact, the expected number of children is infinite. I remember I was an undergraduate, and I first saw an example of a distribution that was always finite but had infinite expectation. And I remember my response. I just laughed and laughed and laughed, and I just, I could follow it line for line, and I saw it was right, but I thought, oh, this is so ridiculous. This is very amusing, but absolutely unimportant. I mean, these are crazy examples. But it turns out, no. It turns out in percolation at the critical point, this behavior where it's finite with probability 1, but the expectation is infinity, it comes up very frequently. It comes up very frequently. Well, here's the exact result. I mean, I won't derive it, but this is the exact result is given by this formula. And if you plug in C equals 1, you get this formula. And if you use Stirling's formula, you see that there is a heavy tail. The probability that the value is u is constant u to the minus 3/2. So the probability that it's greater than or equal to u is constant u to the minus 1/2. On the other hand, for c greater than 1, there is a probability that it's infinite, and it's given by y, where y is the solution to this equation. There's some nice calculus here. Here's the function e to the minus cy, and here's the function 1 minus y, and the value of y is where the two curves intersect. And if c is greater than 1, the e to the minus cy goes under the line, and then it has to cross it at a unique point, and that's actually the probability that it's infinity. Also, for c less than 1, you get c e to the minus c to the u power, and c e to the 1 minus c, because there's an e here. C equals 1. C is less than 1. I forget. Anyway, for c less than 1, you get an exponential tail. Actually, for c greater than 1, you also get an exponential tail, except that there's a probability that it's infinite. So if you exclude the bump at infinity, it also has an exponential tail. Now, what's interesting for us is what does this look like near criticality? That is, suppose that p is 1 plus epsilon. Well, what happens is one can calculate, this is a nice calculus problem. If c is 1 plus epsilon, what are the asymptotics of this intersection point as a function of epsilon? Very nice calculus problem. And the answer is 2 epsilon. As epsilon goes to 0, the asymptotics are 2 epsilon. In fact, there's a Taylor series for it, but it's like 2 epsilon. Now what happens is the probability that it has size u is given by this u to the minus 3/2, but then there's something that's something less than 1, so there's an exponential decay. But the thing is that when c is 1 plus epsilon, this c e to the 1 minus c is like, if c is 1 plus epsilon, it's like e to the minus epsilon squared over 2. Okay. So again, you can write c equals 1 plus epsilon and do the Taylor series for this. In epsilon, you get 1 minus epsilon squared over 2. So its log is like minus epsilon squared over 2. So when you take it to the u power, it only has an effect when u reaches epsilon to the minus 2. So this is the idea. So suppose your Poisson at 1 plus 10 to the minus 6. How is that different from being at criticality? The only difference appears around 10 to the 12. Then this factor starts coming in. So as long as u is small compared to epsilon to the minus 2, you've got a heavy tail. But then, once you reach epsilon to the minus 2, it starts dropping exponentially. So it's sort of, interesting analysis. It's a heavy tail, heavy tail, heavy tail until you reach epsilon to the minus 2, and then it starts really dropping quickly. And like I said before, the graph birth process is like the Poisson birth, except for this ecological limitation, because as every Russian novelist knows, death is inevitable. So you have to stop. Now, one can compare the two models in both directions. That is, suppose you're looking at the actual graph model and you want to say, what is the probability that you generate a component of size at least u? Well, that's bounded from above by the binomial model, because you have an ecological limitation. So if you ignored that limitation, if you simply replaced the points that were deleted, then you would get the binomial birth model. So that provides an upper bound. On the other hand, you also get a lower bound. The probability that you're at least u is at least the probability where instead of binomial n minus 1, you look at binomial n minus u, because then you just think that the reservoir is only n minus u, and you keep on going. And if you reach u, well, you've reached u. So that gives a bound on the other way. So what happens is you can bound the graph process both from above and below by the binomial process, and oftentimes you're able to sandwich the two results. So let me give you kind of a reason. The question everybody asks, why this n to the minus 4/3? Why shouldn't it be n to the minus, 18/13 or something? What, n to the minus 13/18 or whatever. Why is it n to the minus 2/3? And so let me not give a proof, but let me give kind of an argument. So suppose we write p equals 1 plus epsilon over n, and we think of epsilon going to 0. If we look at the Poisson process, the chance that the Poisson process is infinite is like 2 epsilon. Okay, I mean, that comes from the calculation. Now what happens is, in the graph process, you start with a point, and with probability 2 epsilon, it would be going to infinity. Except it's not going to infinity because you only have a finite number of points. What happens is, and okay, this is not a proof. This is what happens is all the points that would have gone to infinity come together and form the dominant component. And that dominant component has size 2 epsilon n. On the other hand, this might be finite. But we said that if it's finite, it really isn't bigger than epsilon to the minus 2. Because once we reach epsilon to the minus 2, it really starts dropping exponentially. So for example, if we said epsilon to the minus 2 times log n, it just wouldn't happen because it's dropping exponentially, and we only have n points to start, so it just wouldn't happen. So basically, the finite components would only go up to size epsilon to the minus 2. Now, in order for this to work, there has to be a dichotomy between the small components and the dominant component. So the dominant component is going to be of size 2 epsilon, and the small components will go up to size epsilon to the minus 2. The only way that will work, the dominant component will have size 2 epsilon n. With probability 2 epsilon, you're in the dominant component. So the dominant component has size 2 epsilon n. The small components go up to size epsilon to the minus 2. In order for this to be a dichotomy, you need epsilon to the minus 2 to be smaller than 2n epsilon, and that gives the n to the minus 1/3. And then since I wrote it 1 plus epsilon over n, we can write it as n to the minus 4/3. Okay. I mean, that's not a proof, but it's an argument for why this exponent n to the minus 4/3 that's so central, why it is that this comes up. Okay. So what happens is, in the barely subcritical region, when epsilon is lambda n to 1 minus epsilon and epsilon is lambda n to the minus 1/3, we bound the chance that you get a component of size u by the Poisson process. But we know that if we have, remember we had the epsilon to the minus 2, if we throw in a log n, and then if we want to be really fine, we want to be even more careful about that. But let's assume log n is negligible for the, if lambdas, there's some delicate things here, but most of the time, let's just throw in the log n. If u is epsilon to the minus 2 times log n, the probability will drop to little o1. Because remember, after the epsilon to the minus 2, it's dropping exponentially quickly. So you throw in a log n, that means it's dropping polynomially quickly. So in particular, it's less than n to the minus 1, which means you only have n to the minus 1 starting points, so it doesn't happen. So what that means is that there's no component that's bigger than epsilon to the minus 2 log n. Okay. And then one can do it more delicately. But now, in the barely supercritical, we want it to be 1 plus epsilon to the n, where epsilon's lambda n to the minus 1/3, and lambda is going to plus infinity. And we make a trichotomy. We say, so we start at a point and we generate the component. And we say it's small if it's epsilon to the minus 2 times log n. Again, right, very, very barely supercritical. We want the log n to be even smaller, but let's leave out that point. And then the large component is the component of size 2 epsilon n. And let's call a component awkward if it was something else. And one way to argue is to show that the chance of getting an awkward component is little o1. Let me give one argument for this. That's an argument that I like. I might be off by a +1. I want to argue this. I want to look at the breadth first search a little bit differently. Normally, breadth first search, we start with a point, and then we look at its neighbors, and we look at its neighbors, and we look at its neighbors. And here, each edge is in with probability p. But I want to, instead of thinking of starting at a point and moving out, I want to think of all the other points as trying to get in. So what I want to say is we start with a point, and all of the other points flip a coin, and with probability p. And with probability p, they're connected to that point. And then if they're not connected to that point, the second time they flip a coin, and again, they join the component. So we're just turning around the analysis of breadth first search. Each point, except for the root, each point flips a coin with probability p until it gets ahead. And if it gets ahead on the 10th time, then that means it joins the component on the 10th attempt. Of course, the component may no longer exist. It may have already died. So that's why it's called fictitious continuation. So then, the chance that a point has not joined the component at time t is binomial n minus 1 times 1 minus p to the t. And if the component has size exactly t, that means that exactly, no more, no less, n minus t points have not joined the component. So one gets this, and now one can do some analysis and show that unless t is really close to 0, or t is very close to 2 epsilon n, this probability is extremely small. See, the binomial, this probability you're taking a big binomial. The only time this probability isn't really small is if the expected value of the binomial is n minus t. And that turns out to occur at exactly 2 epsilon n. So there's some analysis there, and one shows that these awkward components, the middle ground, just simply doesn't occur. So let me, okay. So what happens then is you can actually show that there are no components that are awkward. The points are either in small components or the giant component. The probability that you're in a giant component is 2 epsilon. So the expected number of points in a giant component in giant components are 2 epsilon n. It still leads a sort of strange thing. A priori, it might be possible that with probability 1/2, we had 2 components of size 2 epsilon n, and with probability 1/2, we had no components of size 2 epsilon n, because this is just expectation. But this can be resolved by sprinkling. Sprinkling is where you just add a few extra edges. So if there was some chance that you had 2 components of size 2 epsilon n, then by just adding a few more extra edges, they would join, and then you would have a component of size 4 epsilon n. But we know from calculation that has exponentially small probability of occurring. So because that doesn't occur, then you go back. This argument sounds circular, but it's actually okay. That you won't have, you just won't have 2 components of size 2 epsilon n. Once again, if you had 2 components of size 2 epsilon n, then a little while later you'd have 1 component of size 4 epsilon n, but we know that you don't have that. So there's some argument there. And like I say, I really urge you to do this. You know, computers are fast these days. I mean, if you want, you can subtract or add a 0 here to the number of vertices. But because what we call union find, the union find algorithm is extremely quick, this is almost a linear time algorithm to do this. You add an edge, and then you want to check the component sizes. And what you do is you keep going until you're at lambda equals minus 4, and now you look at the component sizes, you normalize by n to the minus 4/3. You can also look at the complexity, because when you add an edge, if you add an internal edge, the complexity goes up by 1. But if you have 2 components and you join them with an edge, the complexities add. So you can also keep track of complexity. And actually, it's very nice. You just take n equals 5 times 10 to your favorite number and look at it between lambda equals minus 4 and plus 4, and you'll see all these asteroids coming together until you get the dominant component. It's very, very nice. So let me finish with 2 of my favorite quotes. This is a classic one, if you haven't seen it. really wonderful statement of Isaac Newton. If I have seen further, it is by standing on the shoulders of giants. But Peter Winkler, mathematician at Dartmouth in the United States, has another version because he, like I, has worked a great deal with Hungarian mathematicians such as the great Szemerédi and Lovász, and of course Paul Erdős, and many, many others. So he just changed it a little bit in a way that I like. Just change one word. If I have seen further, it is by standing on the shoulders of Hungarians.
When
And,
he invented it when he was on Bell Labs?
He was at Bell Labs, that's right.
When he wrote it?
Hmm?
When he wrote it?
He was at Bell Labs, yeah. He was at Bell Labs. He was at Bell Labs for many years, but now he's at Dartmouth. Yeah, and he said this, and so it's a wonderful feeling. But maybe it reflects that all of us, to do good mathematics, we have to stand on the shoulders of other people, and we should consider that a very good thing. Okay, spasiba.
Does he have any questions?
I have some genuine questions.
Yeah,
If we, you give
yeah, wait. Yeah.
Oh, thank you. I have a general question. You consider the first was Erdős enyi graph, which is full graph in which we decide with some probability to leave this edge or not.
Yeah.
And another example was Hamming graph.
Yes, Hamming graph.
And
the
both
N cube. Yeah.
yes, and both examples are these strongly regular graphs. If its theory holds for any such graph.
Well, that's a very good question. We don't have. We would like to have a general result that if you have some graph that's nearly regular and has some nice properties, then we will get some nice percolation. But we don't have that theorem, yeah. But we would like to, but we don't have it. I mean, here we have some examples, but one has to be a little bit careful because if you're not careful, the graph can be in two components. So, I mean, you could have a graph where each point has degree, p, but it's really only in two halves. And so there won't be a unique giant component. But maybe with some, there's a general theorem, but I don't know.
Maybe a more specific question.
Yeah.
What about the next after Hamming this Johnson graph, the constant weight vectors, and we edge them if they are neighbors in the corresponding schemes?
Can you say that?
For instance, look at the Hamming graph, the graph of 0 and 1s.
Yeah.
Consider only the points which have the weight half of n.
Yeah.
And then we make edges as usual, because they in the Hamming distance they cannot be the distance is even, so a distance 2.
Yeah. Well, that's a very natural question. I have to think about that. Yeah, I don't know. I mean, we worked on the Hamming graph, but is this going to be different? Again, it maybe not. One thing is you should really look at graphs that are transitive, have a transitive automorphism.
Good is
But in this case, you do have this, because you want all vertices to look the same. This would be an excellent example. So you give me something, maybe I won't go to the parade tomorrow. Maybe I'll work on this problem. Spasiba.
More questions? Okay, so we'll come back on Friday.
Okay.
The same time, but not here, in another place. Maybe you.
Yeah, lecture on Friday will be in the main office. It's like over there. I'll send an email and with details before.
And you will tell me. Okay, good. Thank you.